In most of this course, we've dealt with functions. We've learned how to plot them, to differentiate them, to integrate them, and so forth. But in the last lecture, we dealt with vectors. We learned that they're like arrows pointing in a certain direction, that they have a certain length or a magnitude as well. But now, what if that length or that direction should happen to change, let's say with time? Then we have vectors that are not constant, that change with time or perhaps with some other quantity, some other parameter. How do you differentiate them? How do you integrate them? How do you understand them? That's going to be the subject of vector-valued functions, and we're going to cover that next. We are, of course, familiar with scalar-valued functions or ordinary functions. In this, if you give some number t as an input, and if the name of this scalar function is f, then out will come the number f of t, a single number. With a vector-valued function, if you give a number t as input, this vector function, we'll call this v, will produce a vector output, which we'll call v of t. And since we are used to thinking of vectors as arrows, well, it'll have produced this vector, v. If you give a different value of t, then it could produce maybe this vector, a shorter one or a longer one pointing in a different direction perhaps. And so different numbers t as input produce different vectors as output. Of course, these vectors could be in 2-dimension, or they could be in 3-dimension, or they could be in more dimensions. Well, let's take 2 dimensions first. In 2 dimensions, we know that any vector can be written in terms of 2 basis vectors. So v as a function of t can be expressed as f of t times I plus a second function g of t times j. In other words, when you give in the number t, out come 2 numbers, f of t and g of t. That's for a 2-dimensional vector. For a 3-dimensional vector, we'd have, of course, 3 numbers coming out. So v of t would be f of t times the unit vector I plus g of t times the unit vector j plus a third function h of t times the unit vector k. Now these f, g, and h are independent functions. They have no relation with each other. And so as you change t, they will take different values. Vectors that change with time are, of course, extremely common. So here is a ball that is being thrown upwards at a certain angle with a certain speed, and now you see that as time goes on, its speed decreases until it starts coming back to Earth, and then its speed is what it was when it started. We can look at the components of this vector as the ball is thrown up. The horizontal component will not change, but the vertical component will decrease as the ball goes up and will become 0 when the ball stops moving vertically, and then it becomes maximum as the ball comes down. For a particle moving at constant speed in a circle, you can see that the velocity vector retains its length, but its direction keeps changing. We can imagine looking at this velocity vector at slightly different times. To be quite general, let's imagine an arbitrary curve, maybe a piece of wire that's been bent into this shape, and imagine that there's a particle which moves on it at time t1. It's moving in this direction with some speed, so its velocity vector is v at time t1. At a later time, it is here. This is time t2, and the velocity vector is now v of t2. Okay, now let's transport this vector v of t1 so that it's here. So this is v of t1. And let's parallel transport this other vector so that it is here. So now we have a triangle, and obviously by the rule of vector addition that we discussed, this is v of t2 minus v of t1. We're going to define the derivative of v with respect to time to be the difference of the two vectors. So v of t2 minus v of t1 divided by the time that it took to go from one position to the other. And we could write this as delta v divided by delta t. So delta v is this vector over here, the difference of the two vectors, and delta t is the difference of the two times. And this dv by dt becomes delta v by delta t as delta t becomes smaller and smaller. So in other words, if we look at one time and then another time which is very, very close to that, then we will get the derivative of v with respect to time. We could have used basis vectors, of course, in 2 dimensions or 3 dimensions. So this vector, which is f of t I plus g of t j, can be differentiated using the principle that I just discussed over here. That is to say, we take 2 slightly different times, in which case what we'll have over here is df by dt times the unit vector I plus dg by dt times the unit vector j. So if we are given the vector in component form, then all we need to do is differentiate the components. Now, this definition and this definition are exactly the same. Let's see what speed, velocity, and acceleration are in terms of vectors. So if this is some curve along which a particle moves, let's call this position of the particle r, and of course this changes with time. Then r of t, which is called the position vector, can be expressed in terms of the unit vectors, let's say f times I plus g times j, and this f and g are functions of time, as we've discussed. The rate of change of the position vector is what we call the velocity vector, that's dr by dt, and that will be df by dt times I plus dg by dt times j. And from here, the speed, which is v dot v or v squared, this over here is df by dt squared plus dg by dt squared, and this is what we call the square of the speed. So denoting the magnitude of v by this is written as magnitude of v squared, or sometimes people just write it as v squared. If we take the derivative of the velocity vector, so dv by dt, that's what we call, that's actually the definition of acceleration, rate of change of velocity. And in component form, this is d2f by dt squared I plus d2g by dt squared j. These basis vectors are fixed. They do not change. They are fixed to the axes, and so we do not need to consider their variation. Here's a straightforward problem. The coordinates of a particle are x equals sine t, y equals e to the t. We want to know what will be the speed, velocity, and acceleration at t equal to half. So here r is sine t times the unit vector I plus e to the t times the unit vector j, in which case dr by dt, which is the velocity vector, will be cosine of t I plus e to the t j. And the acceleration vector will be the second derivative, so we take one more derivative, d2r dt squared, and that gives minus sine t I plus e to the t j. From here we can get the speed. That speed is v squared equals cos squared t plus e to the t squared, which is e to the 2t. So therefore the speed v will be the square root of this, cos squared t plus e to the 2t. And at t equal to half, well, everywhere we'll just put t equal to half, and that will give us the speed, velocity, and acceleration. Now we are asked, what is the equation of the straight line that is tangent to the above curve at t equal to half? So let's make a rough sketch of this curve. As t increases from 0, sine of t increases from 0 as well. But at t equal to 0, e to the 0 is 1. So here is a graph that's increasing like this. And at t equal to half, this will be the point sine of half, e to the half. There is a straight line that just touches this at this point, and we are asked to find its equation. Now there are only two things that we need to know about a straight line. What is its slope and which point does it pass through? So let's ask, what is dy by dx? Now dy by dx, from a previous lecture or just by thinking of this, is dy by dt divided by dx by dt. And if we differentiate y with respect to t, we get e to the t. And if we differentiate x with respect to t, we get cosine t. And that's e to the half over cosine of half. So that's the slope of this straight line, this dashed line that I've drawn over here. But we also now recognize the fact that it has to touch this point. So the equation of a straight line is y equals the gradient, which is dy by dx, which is e to the half over cosine of half times x plus some constant. Let's call that constant c. Okay, now when y is e to the half, then we have e to the half equals e to the half over cosine of half, and here x is sine half, and so from here we get the value of c, which is e to the half into 1 minus sine half over cosine half, which is tangent of half. And so we have our equation now, y equals e to the half over cosine half x plus c, where c is equal to this thing. We're now going to develop some rules for differentiating vector functions. First, here is a vector function r multiplied by a scalar function f. The derivative of f into r should be df by dt into r plus f into dr by dt. Let's see how this works out. So We'll begin from the definition of d by dt of f of t into r of t, and everything in the brackets is to be differentiated, which means that we'll take what's in the bracket at a slightly later time than t, so f at t plus delta t times r at t plus delta t, and we'll subtract from the original value, that is this, and divide the whole thing by delta t. Now, that's the definition, and as delta t goes smaller and smaller, we'll get to the left-hand side. Well, let's write this in a slightly different form. So write this as f of t plus delta t, r of t plus delta t, so that's exactly the same as above. And then I'm going to subtract from here f of t, r of t plus delta t, and add exactly the same amount to it so that this makes no difference. And then there's only this last term, f of t, r of t, that needs to be written. And this whole thing is then divided by delta t. Now, the advantage of writing it in this way is that I can write now this thing, f of t plus delta t minus f of t, and divide this by delta t, and here there'll be r of t plus delta t. So I've taken the first two terms, and now I'm going to take the last two terms, which is the following, f of t and then r of t plus delta t minus r of t divided by delta t. So we now have an algebraic equality. As delta t goes to 0, this over here approaches the derivative of f with respect to t, so df by dt. This r of t plus delta t will get closer and closer to r of t, and that's because this vector function has been assumed to be continuous. So as delta t becomes smaller and smaller, this will get closer and closer to this. And here we'll get f of t, and this over here is the definition of the derivative of r. So we get dr by dt here. And that's exactly the result that we wanted. So this has been proved. Now note over here that we have dealt with vector functions that have derivatives. And of course, not all vector functions will have a derivative, but if it is sufficiently well behaved, then it will. In exactly the same way, we could prove this, that if I have a sum of two vectors, two vector functions, one is a of t and the other is b of t, then the derivative of the sum is the sum of the derivatives. Now this is so easy that you should be able to prove it yourself. We are now asked to prove that the derivative of the cross product, so d by dt of a cross b, is the derivative of the first cross the second vector plus the first vector cross the derivative of the second vector. And we're going to do it in exactly the same way as we did in the previous proof. So d by dt of a cross b, and of course here a and b are both functions of time. Well, this is by definition a at t plus delta t cross b at t plus delta t minus a at t cross b at time t divided by the small time difference delta t. And now, just as we did before, we'll use that same trick, which is we'll add and subtract the same quantity. And so here I'm going to subtract this. So there's
b of t plus delta t, and then add back the same thing. So a of t cross b of t plus delta t, and then minus a of t cross b of t, divided of course by the time difference actually. And now we can take a at t plus delta t minus a of t out and divide this by delta t, and this whole thing is now crossed with b of t plus delta t. And finally here we have a of t cross this quantity b of t plus delta t minus b of t divided by delta t. Now, as delta t goes to smaller and smaller values, this over here goes to dA by dt. So here is the vector dA by dt cross. Now again, assuming the continuity of b, that b is a smooth vector function, this becomes b at t. And then here we have a of t cross dB by dt. And so that is the correct answer. That's what we were asked to prove. In exactly the same way, we can prove this. So the point is that if you have a product of two things and you take the derivative of the product, then the Leibniz rule, so what we've seen are examples of the Leibniz rule. The Leibniz rule says differentiate the first, keep the second constant, and then keep the first constant, differentiate the second. Let's use the relations that we've discovered to prove that if the speed of a particle is constant, then its acceleration is perpendicular to its velocity. Now, what does that mean, that the speed of a particle is constant and yet it has an acceleration, and that acceleration is perpendicular to its velocity? Well, let's see. So v dot v, that's the length of the vector v, and that's the velocity squared, and that's the speed squared. This is a constant. That's what we are told. Okay, if it's a constant, then we can differentiate with respect to time v dot v, and that has to equal to 0. But now let's recall the rule, which is that this is dv by dt dot v plus v dot dv by dt, and of course the two are exactly the same. So that says that we have v dot dv by dt equals 0. In other words, the velocity and the acceleration vectors are perpendicular. So that's a very important fact. And this says, for example, that if there is a particle that's going around in a circle with constant speed, its velocity is changing, but its speed is constant. In that case, the velocity which is along this circular path is perpendicular to the acceleration. So the acceleration is then directed towards the center of the circle. Here's an example. There's a particle that's going around at constant speed around a fixed center. So it's moving in a circle. This is the velocity vector that you can see over here. And this is the acceleration vector. This is perpendicular to the velocity vector. But the path does not necessarily have to be a circle. Here's a particle that's moving at constant speed, but it's moving
in this curve, which looks like an 8. So again, here is the velocity vector, which is tangent to the curve, and here is the acceleration vector, which is perpendicular to it. We know that we can write any vector in terms of the fixed basis vectors I and j. But sometimes it is useful to have basis vectors that move. Consider this curve over here. It can have any shape. And suppose that there's a particle that moves on it. Here, at this particular time, it is at the point P. Let's call this the origin O. Then the vector from O to P, we shall call that R, and R changes with time. The direction of R is given by the unit vector R hat, and there is a vector also of unit length that is perpendicular to that. So this over here is 90 degrees, and as the point P moves, the unit vector R and the unit vector theta will both move. Let's look at this a little more carefully. So I've parallel transported the vectors so that they are at the origin over here. This angle over here is theta. Now, these unit vectors can be expressed in terms of the unit vectors along the x direction and the y direction. Obviously, this length over here is cosine theta, and this length over here is sine theta. So we can write the unit vector r as cosine theta into the unit vector I, which is along the x direction, plus sine theta into the unit vector along the y direction, which is j. Now let's look at the theta vector, and this angle over here is obviously 90 minus theta. So this distance over here is minus sine theta. Minus because it's on the other side of the y-axis. Now this length over here will be cosine theta, and so we can write the unit vector theta as minus sine theta into I plus cosine theta into j. And now let's check to see if they are actually perpendicular. So r dot theta, you can see this will be cosine theta into minus sine theta plus sine theta into cosine theta, so that is 0, and indeed these are orthogonal to each other. Now as the point P moves, the unit vectors will change. Let's calculate how fast they change. So if I take dr by dt, then I will know how the unit vector r is changing with time. Of course, its length is not changing, but its direction is changing, and so therefore we should compute this derivative. We can write this more compactly as r dot. This dot over here means d by dt. Well, let's compute that looking at what's over here. So if you differentiate cosine theta, you get minus sine theta, and then there's theta dot by the chain rule times the unit vector I, and we don't have to differentiate I because it's fixed. Then there is cosine theta, theta dot j. Similarly, we can compute theta hat dot, and that clearly over here is minus cosine theta, theta dot I, and then minus sine theta, theta dot j. Well, let's slightly rewrite this. So r hat dot, I'm going to write as, I'll take theta dot out, and inside will be minus sine theta I hat plus cosine theta j hat. And now if you look up over here, That's exactly what theta hat is. So this is equal to theta dot theta hat. So the rate of change of the unit vector r is this. Similarly, let's take theta dot out over here, and here we shall find that there's cosine theta I plus sine theta j, which is, of course, minus theta dot r hat. So now we know how the unit vectors change with time. Let's now come over here. Here the vector r is the length r times the unit vector in the r direction. So you see over here that there is no theta that is involved. The vector r is obviously in the direction of the unit vector, and so that's all that we have over here. Let's now compute how r changes with respect to time. So r dot, we have to differentiate this. That'll be r dot into r hat. And then we need to differentiate the unit vector with respect to time. So that's r hat dot. And now r hat dot we already have. That's theta dot theta hat. And so this is r dot r hat plus r theta dot theta hat. This is the velocity of the particle when it is expressed in terms of r and theta, in terms of these moving basis vectors. What about the acceleration? Now this is going to be quite an important formula for physics, so let's compute the second derivative of r, which means we've got to differentiate what we've just derived with respect to time once more. So this is r double dot r hat, and then r dot, we have to differentiate this r hat over here. When differentiated gives us theta dot into theta hat. And now let's differentiate these three terms over here. Well, first we get r dot theta dot. So I've differentiated the r over here, and there's then another differentiation to do with theta dot. So that's r theta double dot theta hat. And then finally we have to differentiate the theta hat, and that gives us minus theta dot r hat. So there's minus r theta dot into theta dot, that's theta dot squared into r hat. So let's now just put things together. Here we will have r double dot minus r theta dot squared r hat, and then there's 2r dot theta dot plus r theta double dot theta hat. And now that's the formula for the acceleration of the particle in these moving basis vectors. Let's now apply the formula that we just derived for the velocity and for the acceleration of a particle that moves around in a circle. Here is the unit radial vector, r hat, and here is the unit vector theta hat, which is perpendicular to that. Now, this angle over here is theta, and clearly as theta increases, the unit vectors are changing direction. Since this is moving in a circle, r is a constant, which means that r dot is 0 and r double dot is also 0. Hence, the velocity r dot will be r theta dot into theta hat, which means that the velocity is tangential to the circle. What about the acceleration? R double dot will be 0, of course. The rate of change of the length will be 0. So what we have is minus r theta dot squared in the radial direction, and then r theta double dot in the theta direction. Now, if theta dot is a constant, so that's only an if, which means that if it is moving around at a constant rate, that is to say theta is increasing with time linearly, then the acceleration will be directed towards the center and its magnitude will be r theta dot squared. So that's if theta dot is a constant, it'll be minus r theta dot squared and directed inwards. Here is a particle that's moving in a circle, and you can see that this is the velocity vector over here, and this is the acceleration. The acceleration is pointing towards the center of this circle, and the velocity is tangential, exactly as we had derived. We've learned how to differentiate vector-valued functions, but can we also integrate vector-valued functions? In other words, what would an integral like this, integral dt v of t from, let's say, t1 to t2 mean? What's the meaning that we can give to this? Now, imagine that there's a curve, an arbitrary curve that looks like this. Some particle moves on this. So here is the particle at time t1. Its velocity vector at time t1 is this. At a later time t2, it's here. Its velocity vector is v at t2. And then at a still later time, it's at this point over here. Its velocity vector here is v of t3. Now, let's say that it took time delta t1 to go from here till here, delta t2 time to go from here till here, and then delta t3 time to go from here till here. So now let's add up delta t1 v of t1 plus delta t2 v of t2 plus delta t3 v of t3. We can make a diagram of this. Here is the vector v of t1, and let's multiply this by delta t1. So this is delta t1, v at t1, etc. Now these are vectors which can therefore be added together. The sum of two vectors is a vector, and then you add that to the third vector, and that's also a vector. And they have a resultant. That resultant is this. Now imagine that we were to take lots and lots of these delta t's and multiply by v's and then sum all of them up. The result of this, in the limit that delta t goes to 0, will be the integral of v of t, and of course the integration limits can be from anywhere to anywhere. Now that's the meaning of the integral of this vector valued function. You can always write v of t in terms of basis vectors, so we could write this as, let's say, some function f of t times the unit vector I plus g of t times the unit vector j. If this is in 2 dimensions, if it's in 3 dimensions, you'll add to this h of t times the unit vector k. And of course, I'm taking fixed basis vectors over here. I could have even taken moving basis vectors. But in that case, this thing will be the integral of f of t from t1 to t2 plus j integral from t1 to t2 of g of t, etc. And finally this. So we can just integrate the components if we like, and that has the same meaning. Of course, you may not want to break this up into components. There might be some easier way of doing things, but you can always take a vector, break it up into components, and then the integral becomes the integral of the components. Let's do a couple of examples. First, we'll integrate the vector valued function v, which is sine t times the unit vector I plus t squared times the unit vector j. And this is easily done. We'll take the unit vector outside, dt, 0 to pi, sine t inside, and then j dt, 0 to pi, t squared. This integral is trivially done. Integral of sine t from 0 to pi. You can do this mentally, in fact. This is just 2i, and this over here will be pi cubed by 3j. Now let's go to another example. Here's the vector valued function of theta, and this vector is just the position vector from the origin. So let's first of all integrate this over theta from 0 to pi, and there's I cosine theta plus j sine theta, and again these integrals are trivial. The integral of cosine theta from 0 to pi is 0 because it's as much positive as negative, and so this is just the integral of sine theta, that's 2j. But how do we think about this? So let's see that this over here is the position vector of a point that lies on a circle, or rather a semicircle over here. So the particle goes around on a semicircle like this, and this is its position vector r. And this is a function of this angle theta over here. Now what we're doing is adding up these vectors r at different values of theta. And let's recall that we can break up this vector into a component that's along the x direction and a component that's along the y direction. As theta changes, its component along the x direction is initially positive, then becomes negative, and the positive and the negative parts cancel each other out, whereas the part along the y direction does not. And so you get 2 units along the y direction and 0 units along the x direction. Finally, we are asked to prove this relation over here, which says that the derivative with respect to t of this vector valued integral up till the limit t is that function a of t itself. The best way to look at this is to think of this thing over here as being a function of t, a vector valued function of t. So d by dt of f of t then means that you take the function at t plus delta t minus the function at t divided by delta t, and then delta t is to become as small as possible. Now let's take this thing over here. So that's the integral from a till t plus delta t of the
vector valued function a minus the integral from a to t of that same thing divided by delta t. Now let's recall that if I have an integral which goes from a to b, then that's the same as the integral from b to a with the sign reversed. So let's then write this as integral a to t plus delta t, and this has been left unchanged, but this over here is now from t to a. The sign has been reversed, and now we'll use the fact that if I have an integral from, let's say, a to b, and then an integral from b to c, then this is the same as the integral from a to c. So here I'm going from t to a and a to t plus delta t. So this is the integral then from t to t plus delta t of a of s. Now notice, and of course we have to divide by delta t everywhere, and so there's the 1 over delta t here. Now notice that a has disappeared altogether. The interval of integration is getting smaller and smaller, and so this becomes simply delta t times a of t divided by delta t, and that is a of t. So the point is that as delta t gets smaller and smaller, the integrand varies less and less, and of course here I've assumed that a is a function that is a vector valued function that is smooth, continuous, and so its values tend to a of t. This is the result that we wanted.
In this lecture, we saw that dealing with vector valued functions is not very different from dealing with ordinary functions in terms of differentiation, integration, etc. But the important message that you should take away from this lecture is that there are two equivalent ways of looking at vector valued functions. One is in terms of bases, and so that's algebraic, and the other is in terms of geometry. Both ways are useful, sometimes one, sometimes the other. Looking at the same thing in two different ways always gives you much deeper insight, and that's how mathematicians and physicists should always look at problems.